Hot melt adhesive, also known as hot glue, is a form of thermoplastic adhesive that is commonly supplied in solid cylindrical sticks of various diameters, designed to be melted in an electric hot glue gun. The gun uses a continuous duty heating element to melt the plastic glue, which may be pushed through the gun by a mechanical trigger mechanism, or directly by the user. The glue squeezed out of the heated nozzle is initially hot enough to burn and even blister skin. The glue is tacky when hot, and solidifies in a few seconds to 1 minute. Hot melt adhesives can also be applied by dipping or spraying. In industrial use, hot melt adhesives provide several advantages over solvent-based adhesives. Volatile organic compounds are reduced or eliminated, and the drying or curing step is eliminated. Hot melt adhesives have long shelf life and usually can be disposed of without special precautions. Some of the disadvantages involve thermal load of the substrate, limiting use to substrates not sensitive to higher temperatures, and loss of bond strength at higher temperatures, up to complete melting of the adhesive. This can be reduced by using a reactive adhesive that after solidifying undergoes further curing, for example, by moisture, or is cured by ultraviolet radiation. Some HMAs may not be resistant to chemical attacks and weathering. HMAs do not lose thickness during solidifying. Solvent-based adhesives may lose up to 50 to 70% of layer thickness during drying. Glue stick diameters, 1 a 4-inch, 5 a 16-inch, 7 a 16-inch, 1 a 2-inch, 5 a 8-inch, 1-inch slug, 1 3 a 4 inches slug, diameters 0.50 inch and smaller are typically used for home and craft. The smaller diameter allow for more rapid heating. Note that many of the smaller sizes are similar. An incorrect size will strip in trigger-fed guns rather than advancing correctly. The standard label on glue stick packaging is only a marketing term, not a legal or industry-regulated dimensional guarantee. Diameters above 0.50 inch are usually used in industrial settings to decrease the stick feed rate for a given volume of material. Rapid heating is not a concern as the process will continue long enough that a longer start time is of little concern over repeatedly having to load new material. Note that for paintless dent repair, sub 0.50 inch sticks are used, no doubt for the more rapid heating time. Hot melt specific properties. Melt viscosity, one of the most noticeable properties, influences the spread of applied adhesive, and the wetting of the surfaces. Temperature dependent. Higher temperature lowers viscosity. Melt flow index, a value roughly inversely proportional to the molecular weight of the base polymer. High melt flow index adhesives are easy to apply but have poor mechanical properties due to shorter polymer chains. Low melt flow index adhesives have better properties but are more difficult to apply. Pot life stability, the degree of stability in molten state, the tendency to decompose and char. Important for industrial processing where the adhesive is molten for prolonged periods before deposition. Bond formation temperature, minimum temperature below which sufficient wetting of substrates do not occur. General adhesive properties, open time, the working time to make a bond, where the surface still retains sufficient tack, can range from seconds for fast-setting HMAs to infinity for pressure-sensitive adhesives. Set time, time to form a bond of acceptable strength. Tack, the degree of surface stickiness of the adhesive. Influences the strength of the bond between wetted surfaces. Surface energy, which influences wetting of different kind of surfaces. Materials used, hot melt glues usually consist of one base material with various additives. The composition is usually formulated to have a glass transition temperature below the lowest surface temperature and a suitably high melt temperature as well. The degree of crystallization should be as high as possible but within limits of allowed shrinkage. The melt viscosity and the crystallization rate can be tailored for the application. Faster crystallization rate usually implies higher bond strength. To reach the properties of semicrystalline polymers, amorphous polymers would require molecular weights too high and, therefore, unreasonably high melt viscosity. The use of amorphous polymers in hot melt adhesives is usually only as modifiers. Some polymers can form hydrogen bonds between the chains, forming pseudo-cross links strengthening the polymer. The nature of the polymer and tackifier additive influences the nature of mutual molecular interaction and interaction with a substrate. For example, the EVA together with terpenphenol resin tackifiers display acid-base interactions between the carbonyl groups of vinyl acetate and hydroxyl groups of TPR. Complexes are formed between phenolic rings of TPR and hydroxyl groups on the surface of aluminium substrates, and interactions between carbonyl groups and silanol groups on surfaces of glass substrates are formed. Polar groups, hydroxyls and ene groups can form acid-base and hydrogen bonds with polar groups on substrates like paper or wood or natural fibers. Non-polar polyolefin chains interact well with non-polar substrates. Good wetting of the substrate is essential for forming a satisfying bond between the adhesive and the substrate. More polar compositions tend to have better adhesion due to their higher surface energy. Amorphous adhesives deform easily, tending to dissipate most of mechanical strain within their structure, passing only small loads on the adhesive-substrate interface. Even a relatively weak non-polar surface interaction can form a fairly strong bond prone primarily to a cohesive failure. The distribution of molecular weights and degree of crystallinity influences the width of melting temperature range. Polymers with crystalline nature tend to be more rigid and have higher cohesive strength than the corresponding amorphous ones, but also transfer more strain to the adhesive-substrate interface. Higher molecular weight of the polymer chains provides higher tensile strength and heat resistance. Presence of unsaturated bonds makes the adhesive more susceptible to autooxidation and UV degradation and necessitates use of antioxidants and stabilizers. The adhesives are usually clear or translucent, colorless, straw-colored, tan, or amber. Pigmented versions are also made. Materials containing polar groups, aromatic systems, and double and triple bonds tend to appear darker than non-polar fully saturated substances. When a water-clear appearance is desired, suitable polymers and additives, for example hydrogenated tackifying resins, have to be used. Increase of bond strength and surface temperature can be achieved by formation of crosslinks in the polymer after solidification. This can be achieved by using polymers undergoing curing with residual moisture, exposition to ultraviolet radiation, electron irradiation, or by other methods. Resistance to water and solvents is critical in some applications. For example, in textile industry, resistance to dry cleaning solvents may be required. Permeability to gases and water vapor may or may not be desirable. Non-toxicity of both the base materials and additives and absence of odors is important for food packaging. Mass consumption disposable products such as diapers necessitate development of biodegradable HMAs. Research is being performed on, for example, lactic acid polyesters, polycarbolate with soy protein, etc. Some of the possible base materials of hot melt adhesives include the following: ethylene vinyl acetate copolymers, low performance, the low cost and most common material for the glue sticks. They provide sufficient strength between 30 and 50 degrees Celsius but are limited to use below 60–80 degrees Celsius and have low creep resistance under load. The vinyl acetate monomer content is about 18–29% by weight of the polymer. High amounts of tackifiers and waxes are often used. An example composition is 30–40% of EVA copolymer, 30–40% of tackifier resin, 20–30% of wax, and 0.5–1% of stabilizers. Fillers can be added for special applications. Can be formulated for service temperatures ranging from a 40 to plus 80 degrees Celsius, and for both short and long open times and a wide range of melt viscosities. High stability at elevated temperatures and resistance to ultraviolet radiation, which can be further enhanced with suitable stabilizers. High vinyl acetate content can serve for formulating a hot melt pressure-sensitive adhesive. EVA formulations are compatible with paraffin. EVA was the base for the original hot melt composition. The composition of the copolymer influences its properties. Increased content of ethylene promotes adhesion to non-polar substrates such as polyethylene, while increased content of vinyl acetate promotes adhesion to polar substrates such as paper. Higher ethylene content also increases mechanical strength, block resistance, and paraffin solubility. Higher vinyl acetate content provides higher flexibility, adhesion, hot tack, and better low-temperature performance. Adhesive-grade EVA usually contains 14 to 35% vinyl acetate. Lower molecular weight chains provide lower melt viscosity, better wetting, and better adhesion to porous surfaces. Higher molecular weights provide better cohesion at elevated temperatures and better low-temperature behavior. Increased ratio of vinyl acetate lowers the crystallinity of the material, improves optical clarity, flexibility and toughness, and worsens resistance to solvents. EVA can be cross-linked by, for example, peroxides, yielding a thermosetting material. EVAs can be compounded with aromatic hydrocarbon resins. Grafting butadiene to EVA improves its adhesion. Its dielectric properties are poor due to high content of polar groups, the dielectric loss is moderately high. Polypropylene HMAs are a better choice for high-frequency electronics. EVAs are optically clearer and more gas and vapor permeable than polyolefins. Nearly half of EVA HMAs is used in packaging applications. Cryogenic grinding of EVAs can provide small, water-dispersible particles for heat seal applications. EVA can degrade primarily by loss of acetic acid and formation of a double bond in the chain, and by oxidative degradation. EVA can be compounded into a wide range of HMAs, from soft pressure-sensitive adhesives to rigid structural adhesives for furniture construction. Ethylene acrylate copolymers have lower glass transition temperature and higher adhesion even to difficult substrates than EVA. Better thermal resistance, increased adhesion to metals and glass. Suitable for low-temperature use. Ethylene vinyl acetate maleic anhydride and ethylene acrylate maleic anhydride topolymers offer very high performance. Examples are ethylene N-butyl acrylate, ethylene acrylic acid and ethylene ethyl acetate. Polyolefins, atactic polypropylene, pilibutene-1, oxidized polyethylene, etc., low performance, for difficult-to-bond plastics. Very good adhesion to polypropylene, good moisture barrier, chemical resistance against polar solvents and solutions of acids, bases, and alcohols. Longer open time in comparison with EVA and polyamides. Polyolefins have low surface energy and provide good wetting of most metals and polymers. Polyolefins made by metallocene catalyzed synthesis have narrow distribution of molecular weight and correspondingly narrow melting temperature range. Due to the relatively high crystallinity, polyethylene-based glues tend to be opaque and, depending on additives, white or yellowish. Polyethylene hot melts have high pot life stability, are not prone to charring, and are suitable for moderate temperature ranges and on porous non-flexible substrates. Nitrogen or carbon dioxide can be introduced in the melt, forming a foam which increases spreading and open time and decreases transfer of heat to the substrate, allowing use of more heat-sensitive substrates. Polyethylene-based HMAs are usually used. Foamable HMAs are available on the market since 1981. Amorphous polypropylene HMAs have good dielectric properties, making them suitable for use at high frequencies. PE and APP are usually used on their own or with just a small amount of tackifiers and waxes. The molecular weight of the polymer is usually lower. Lower molecular weights provide better low-temperature performance and higher flexibility. Higher molecular weights increase the seal strength, hot tack, and melt viscosity. Pilibutene-1 and its copolymers are soft and flexible, tough, partially crystalline, and slowly crystallizing with long open times. The low temperature of recrystallization allows for stress release during formation of the bond. Good bonding to nonpolar surfaces, worse bonding to polar ones. Good for rubber substrates. Can be formulated as pressure-sensitive. Amorphous polyolefin polymers are compatible with many solvents, tackifiers, waxes, and polymers. They find wide use in many adhesive applications. APO hot melts have good fuel and acid resistance, moderate heat resistance, are tacky, soft and flexible, have good adhesion and longer open times than crystalline polyolefins. APOs tend to have lower melt viscosity, better adhesion, longer open times and slow set times than comparable EVAs. Some APOs can be used alone, but often they are compounded with tackifiers, waxes, and plasticizers. Examples of APOs include amorphous propylene, amorphous propylene ethylene, amorphous propylene butene, amorphous propylene hexane, amorphous propylene butene. APP is harder than APE, which is harder than APB, which is harder than APH, in accordance with decreasing crystallinity. APOs show relatively low cohesion. The entangled polymer chains have fairly high degree of freedom of movement. Under mechanical load, most of the strain is dissipated by elongation and disentanglement of polymer chains, and only a small fraction reaches the adhesive substrate interface. Cohesive failure is therefore a more common failure mode of APOs. Polyamides and polyesters, high performance, polyamides, high performance, for severe environments. High temperature glues. Typically applied at over 200 degrees Celsius, but can degrade and char during processing. In molten state can somewhat degrade by atmospheric oxygen. High application temperature. High range of service temperatures, generally showing adequate bonding from -40 to 70 degrees Celsius. Some compositions allow operation to 185 degrees Celsius if they do not have to carry load. Resistant to plasticizers, therefore suitable for gluing polyvinyl chloride. Only polyamides derived from secondary diamines however provide a satisfying bond. Resistant to oils and gasoline. Good adhesion to many substrates such as metal, wood, vinyl, ABS, and treated polyethylene and polypropylene. Some formulations are UL approved for electrical applications requiring reduced flammability. 3 groups are employed, with low, intermediate, and high molecular weight. The low MW1s are low temperature melting and easy to apply, but have lower tensile strength, lower tensile shear strength, and lower elongation than the high MW1s. The high MW1s require sophisticated extruders and are used as high-performance structural adhesives. The presence of hydrogen bonds between the polymer chains gives polyamides a high strength at even low molecular weights, in comparison with other polymers. Hydrogen bonds also provide retention of most of the adhesive strength up almost to the melting point. However, they also make the material more susceptible to permeation of moisture in comparison with polyesters. Can be formulated as soft and tacky or as hard and rigid. Niche applications, together with polyesters taking less than 10% of total volume of hot melt adhesives market. Absorption of moisture may lead to foaming during application as water evaporates during melting, leaving voids in the adhesive layer which degrade mechanical strength. Polyamide HMAs are usually composed of a dimer acid with often 2 or more different diamines. The dimer acid usually presents 60 to 80% of the total polyamide mass, and provides amorphous nonpolar character. Linear aliphatic amines such as ethylene diamine and hexamethylene diamine provide hardness and strength. Longer chain amines such as diamine reduce the amount of hydrogen bonds per volume of material, resulting in lower stiffness. Polyether diamines provide good low-temperature flexibility. Piperazine and similar diamines also reduce the number of hydrogen bonds. Only polyamides based on piperazine and similar secondary amines form satisfactory bond with polyvinyl chloride. Primary amines form stronger hydrogen bonds within the adhesive, secondary amines can act only as proton acceptors, don't form hydrogen bonds within the polyamide, and are therefore free to form weaker bonds with vinyl, probably with the hydrogen atom adjacent to the chlorine. Polyesters, similar to the ones used for synthetic fibers. High application temperature. Synthesized from a diol and a dicarboxylic acid. The length of the diol chain has major influence to the material's properties. With increasing diol chain length the melting point increases, the crystallization rate increases, and the degree of crystallization decreases. Both the diol and acid influence the melting point. In comparison with similar polyamides, due to absence of hydrogen bonds, Polyesters have lower strength and melting point, but are much more resistant to moisture, though still susceptible. In other parameters, and in applications where these factors do not play a role, polyesters and polyamides are very similar. Polyesters are often used for bonding fabrics. They can be used on their own, or blended with large amounts of additives. They are used where high tensile strength and high temperature resistance are needed. Most polyester hot melt adhesives have high degree of crystallinity. Niche applications, together with polyamides taking less than 10% of total volume of hot melt adhesives market. Water dispersible amorphous polymers, modified by addition of sodium sulfonate groups for dispersibility, were however developed for repulpable adhesives. Polyesters are often highly crystalline, leading to narrow melting temperature range, which is advantageous for high-speed bonding. Polyurethanes, thermoplastic polyurethane offer good adhesion to different surfaces due to presence of polar groups. Their low glass transition temperature provides flexibility at low temperatures. They are highly elastic and soft, with wide possible crystallization and melting point ranges. Polyurethanes consist of long linear chains with flexible, soft segments alternating with rigid segments. The rigid segments form hydrogen bonds with rigid segments of other molecules. Higher ratio of soft to hard segments provides better flexibility, elongation, and low temperature performance, but also lower hardness, modulus, and abrasion resistance. The bonding temperature is lower than with most other HMAs, only about 50 to 70 degrees Celsius, when the adhesive behaves as a soft rubber acting as a pressure-sensitive adhesive. The surface wetting in this amorphous state is good, and on cooling the polymer crystallizes, forming a strong flexible bond with high cohesion. Choice of a proper disocyanate and polyol combination allows tailoring the polyurethane properties. They can be used on their own or blended with a plasticizer. Polyurethanes are compatible with most common plasticizers, and many resins. Polyurethanes, or reactive urethanes, for high temperatures and high flexibility. New type of hot melt thermosetting adhesives, introduced in early 1990s. Solidification can be rapid or extended in range of several minutes. Secondary curing with atmospheric or substrate moisture then continues for several hours, forming crosslinks in the polymer. Excellent resistance to solvents and chemicals. Low application temperature, suitable for heat-sensitive substrates. Heat resistant after curing, with service temperatures generally from -30 degrees Celsius to +150 degrees Celsius. Ink solvent resistant. Often used in bookbinding, automotive, aerospace, filter and plastic bag applications. Susceptible to UV degradation causing discoloring and degradation of mechanical properties, requires blending with UV stabilizers and antioxidants. Usually based on prepolymers made of polyols and methylene diphenyl disocyanate or other disocyanate, with small amount of free isocyanate groups. These groups when subjected to moisture react and cross-link. The uncured solidified green strength tends to be lower than non-reactive HMAs, mechanical strength develops with curing. Green strength can be improved by blending the prepolymer with other polymers. Styrene block copolymers, also called styrene copolymer adhesives and rubber-based adhesives, have good low-temperature flexibility, high elongation, and high heat resistance. Frequently used in pressure-sensitive adhesive applications, where the composition retains tack even when solidified. However, non-pressure sensitive formulations are also used. High heat resistance, good low-temperature flexibility. Lower strength than polyesters. They usually have ABA structure, with an elastic rubber segment between two rigid plastic end blocks. High-strength film form as a stand-alone, increase cohesion and viscosity as an additive. Water-resistant, soluble in some organic solvents. Cross-linking improves solvent resistance. Resins associating with end blocks improve adhesion and alter viscosity. Resins associating to the mid-blocks improve adhesion, processing and pressure-sensitive properties. Addition of plasticizers reduces cost, improves pressure-sensitive tack, decrease melt viscosity, decrease hardness, and improve low-temperature flexibility. The ABA structure promotes a phase separation of the polymer, binding together the end blocks, with the central elastic parts acting as cross-links. SBCs do not require additional cross-linking. Styrene butadiene styrene, used in high-strength PSA applications, styrene isoprene styrene, used in low-viscosity high-tack PSA applications, styrene ethylene butylene styrene, used in low-self-adhering non-woven applications, styrene ethylene propylene. Polycarprolactone with soy protein, using coconut oil as plasticizer, a biodegradable hot melt adhesive investigated at Korea University. Polycarbonates, fluoropolymers, with tackifiers and ethylene copolymer with polar groups, silicone rubbers, undergo cross-linking after solidification, form durable flexible UV and weather-resistant silicone sealant. Thermoplastic elastomers, polypyrrole, a conductive polymer, for intrinsically conducting hot melt adhesives, used for ME shielding. EVA compounded with 0.1-0.5 Wt. %PPY are strongly absorbing in near-infrared, allowing use as near-infrared activated adhesives. Various other copolymers, the usual additives include the following: tackifying resins, hydrogenated hydrocarbon resins, and their mixtures, terpenphenol resins, up to about 40%. Tackifiers tend to have low molecular weight, and glass transition and softening temperature above room temperature, providing them with suitable viscoelastic properties. Tackifiers frequently present most of both weight percentage and cost of the hot melt adhesive. Waxes, for example, microcrystalline waxes, fatty amide waxes or oxidized Fischer-Tropsch waxes. Increase the setting rate. One of the key components of formulations, waxes lower the melt viscosity and can improve bond strength and temperature resistance, plasticizers, antioxidants and stabilizers. Added in small amounts,